So the crack is on the XZ plane, right? But when we calculate our Q and our I, we are calculating on a YZ plane, right? So this is where things get confusing. Why the area of consideration where the crack growth is different, right? So let me touch on. So if we have a specimen like this, right? And when we have a tensile load P, right? The area of interest, this is the area of interest, right? So when we calculate, so when fracture will also occur on this surface. So stress is equal to P over A, right? But for this case, if you look at shear, the shear did not occur on the what? On the plane, there's a YZ plane. The shear, which I counted, paint in yellow. The shear occur along this plane, along the, as mentioned before, along the exact plane, right? So what is going on? Okay, so the first thing about shearing stress is a lot of times people get really confused. Okay, if the fracture is occurring on the or if the fracture is occurring on the exact plane, so this one I'll label it as this is on the exact plane, right? Why is it the first moment of area we calculate is on the YZ plane, whereas the fracture is on the XZ plane? Okay, so this can be explained very easily. Okay, why I'm going to this stage is you have to visualize this, or not it does not make sense. Like, hey, does not make sense. The area you can see, right? The area that or the area that we consider the first and second moment of area is not the same as the one on the exact plane. Okay, so I'm going to draw the schematic. I'm going to sketch the schematic. I'm going to sketch the schematic of a cantilever beam. Under a point load. So now I'm going to sketch our transformation. This is X, this is Y, rotation about Z, and then the wall is built in. The structure is built into the wall. And then from here, we have a beam. So we have point A and point B. And then we have a load applied over here, which I'll call this Vy. So when we calculate our first moment of area, second moment of area, we consider this area that I highlight in yellow. Right. So this is the plane in which the Q and I are formulated. Okay. Then I'm going to draw some. So we're going to assume that the structure has layers. Okay, this is a schematics. Schematic means I'm going to use this form to explain to you a theory so you can understand better. So imagine the structure is made of layers. Okay. So when you have a shear force applied on the end, okay. So next we look at the deformation pattern. Okay. So point A. So how the structure will deform? The structure will deform this way. Okay. And then I'm going to place some of this one, right? So all the layers will fill. You can see the layers. Right, layer by layer. Okay. And then I'm going to, sorry. So I'm going to draw this closing this way. And the last one, okay, this way, right? So what I'm going to do now is I'm going to draw the exploded view of over here. Okay, the exploded view of here. So I'm going to magnify. So when I magnify, it looks like this. Okay, so this is the magnified region. So what you will see is you will see a change in length on this plane. You will see a change. So you'll see that you have a delta over here. And in this orientation, the height did not really change. Right? So if you look at this surface over here, if you were to look at this plane over here, the one I draw in pink, right, where slip occur, right, is in fact the horizontal line I'm drawing in pink. And that is the same thing that I sketch in pink, which is along your XZ plane. Okay. But that still don't, then you're still confused, or we're still confused. Then why are we analyzing on the yellow surface? Right? Why are we analyzing on a yellow surface? So this is because, and you guys don't know yet, okay? So if we were to look into shearing stress, acting on the element, okay? So if I were to draw an element now, okay, and our element, this is our X and this is our Y. Based on how the structure is loaded, we will have shearing stress acting in this direction. Okay. So over here, the arrow, so I will still use the so-called our yellow. Yellow means the in the, so I will call, so this yellow one is on the what? This yellow one is, I'm looking at on 3D. It is our YZ plane. I want to be sure, did I get it right the first time? Yeah, YZ plane. And the pink one, the pink line, or the pink surface, this is for our, wait, this is on our XZ plane. And if you look at this arrow over here, this arrow is shear, right? The plane is intersecting the x-axis and the direction is in the y. And over the other side, this arrow over here is shear. The plane will be intersecting the y-axis, and the shear force or the arrow is pointing the x direction. So in terms of shearing stress, we make the assumption, right? We make the assumption that for shearing stress, okay, in a state of equilibrium, shear xy is equal to shear yx. Okay, so whatever you calculate on, so the shear on the yz plane is equal to the shear on the xz plane. Okay, so this is for this reason, right? For this reason, and for this reason alone, that is why, right, when we calculate the first moment and second moment of area, we calculate on the what? We calculate on the on this plane over here, which is our YZ plane. Okay, YZ plane. However, the fracture occur on the what? XZ plane. So I will call this fracture. Okay, because in the state of equilibrium, the shear in the XY direction is equal to the shear in the YZ. Okay, so the first so this looks a bit confusing, and I now explain to you what is it. So the first X is the intersecting plane. Okay, so what do I mean by the or not intersecting plane? I should call this, I will write longer. So this is the plane intersecting the transformation. So if you look at the yellow plane, right? The yellow plane is intersecting the x-axis, right? If I draw the yellow plane now and I highlight in yellow, right? It's intersecting the what? The x-axis. So this is the first x. The y, the next y that you see over here, okay, it is the shear stress direction or orientation. So the shear stress orientation is pointing in the y-axis. If you look at the shear y-axis, right, the intersecting plane now is horizontal now. Okay, so the plane intersect the transformation about the y-axis. So that's why this is y, and the shear stress is flowing in the x direction. Okay, so that's how the nomenclature work. Okay, so if we were to look into the formula now, if we were to look at into the general formula, right, for shear. So the shear stress is equal to Vy over Izz Qz over T. So this is the general formula. And plus or minus, okay, Vz over Iyy Qy over T, right? Now this is opposite from our bending moment, right? So in terms of bending moment, right? So in terms of bending moment, we have plus or minus my over what? Iyy, right? Multiplied by z plus minus by mz over izz multiplied by y. In shear, if your shear force is in the y direction, right, you have to consider the izz axis. Okay. So what do I mean by that? So if we now were to look into the cross-sectional view, okay, so this is our cross-sectional view. So this is y and this is z. So if our shear force